In this lesson, you will be introduced to the idea of mechanical power. Okay, let's begin with a recap. Go back to an earlier problem where Nicholas was pushing his shopping trolley around the supermarket, and we worked out how much work he did. On your screen, you can see a recap of that problem, and we worked out that applying a force of 50 newtons for 300 meters, he did 15,000 joules of work, mechanical work. So, with that in mind, I'd like you to ponder 2 or 3 questions. Try to answer them in your head before looking at the solution. Firstly, would it matter whether Nicholas had completed his shopping journey in 10 minutes or 20 minutes? Would it make any difference to the physics of the situation? Well, the answer is yes, it does matter. The 2 situations are not physically the same because one takes 10 minutes and one takes 20 minutes. Next question. Would he have done the same amount of work each time? In other words, if he pushed the shopping trolley around with that force in 20 minutes, would he have done the same amount of work as if he had pushed it round in 10 minutes? Well, the answer is yes. He would have done exactly the same amount of work each time, because if you look at the work done equation, work done is applied force times distance, time is not involved in the equation. So interestingly, it doesn't matter how quickly he does this work, if the force is the same and the distance is the same, he is doing the same amount of work no matter how long it takes. Final question then. So what is physically different if he does the same amount of work in a shorter time? Surely there must be some difference in physics between the 2 situations. Well, when he does the work in a shorter time, his rate of doing the work is greater. And that's really the core of what we are investigating in this lesson. The idea of a rate brings us to the concept of mechanical power. Well, we define mechanical power as the rate of doing work. Power is the rate of doing work. In physics, when we say the word rate, you can think of it as simply meaning per second. Rate just means per second. So, we can think of power as the amount of work done per second, or the rate of doing work. And it's quite common to hear a definition of power as the rate of doing work. As a word equation, that then becomes power equals work done divided by time taken. And as a symbolic equation, P equals EW over T. Power is work done divided by time taken. Units, well, we always measure work done in joules, not kilojoules, not megajoules, always joules. We always measure time in seconds, not minutes or hours. And if we have our work done in joules and our time in seconds, our power will be in watts. So this is a new unit, the watt, capital W, named after James Watt, the Scottish engineer. 1 watt basically is 1 joule per second. So if you do 1 joule of work every second, your power output is 1 watt. And a typical low energy light bulb nowadays would have a power output of about 10 watts. Okay, let's do an example. Right, let's go back to our shopping trip again. There you can see it on the upper right of your screen. Nicholas pushes his shopping trolley around, 50 Newton force applied, covers 300 metres. He did 15,000 joules of work. Let's assume that he took the longer time of 20 minutes. Let's find his power output. Okay, so before you see the solution, as always, pause the video and try this yourself, and then look at the solution. Well, of course, the first thing we do is we list the variables. We are asked for power output, so we need to know that the symbol for power is capital P. That's a question mark. We already know the work done from a previous calculation. That's 15,000 joules. And we're told that the time taken is 20 minutes. Now, before we go any further, something very important here. Look at that time. Are we going to leave it as 20 minutes? Well, the answer is no, because in the power equation, time must be measured in seconds. So we convert 20 minutes into seconds. There are 60 seconds in each minute. So 20 minutes with 60 seconds in each minute gives us a total time of 1200 seconds. It's vital that you convert that time into seconds. A classic howler in tests and exams is to forget to convert the time into seconds, and you lose marks. Okay, let's state our equation. Power equals work done divided by time taken. That's 15,000 joules of work divided by the 1200 seconds. And that gives us a power output of 12.5 watts. We say that Nicholas's power output was 12.5 watts. He had given out 12.5 joules of energy every second. He was converting 12.5 joules of chemical energy from his body into 12.5 joules of kinetic energy in the movement of the shopping trolley. 12.5 watts is roughly about the power output of a typical low-energy domestic light bulb. That's quite a low power output for a person. Why is that? Well, it's because 15,000 joules isn't really an awful lot of work, to be honest. 1 joule is a really tiny amount of energy on an everyday scale, and even 15,000 joules is not that much. We now come to what in the lab is done as an experiment, one you would do yourself. What it basically involves is climbing up the stairs from the ground floor of the Clavius building all the way up to the 3rd floor to the physics labs, as you can see in the diagram. What I normally do is I lower a measuring tape out of the lab window and get one of you to secure it on the ground, and you might be surprised to learn that the height is 10 meters from the ground up to the floor of the physics lab. Most people estimate it to be a lot more than 10 meters, but when you look vertically downwards, your psychology always causes you to estimate much larger heights. So in the experiment, if you look at the diagram of the boy going upstairs, you can see that you start off at the ground floor and you walk up the stairs briskly to the 3rd floor. And one of your classmates is up at the top, timing you with a stopwatch. Okay, you need to know your mass m to do this, so we weigh you on scales. You're ascending a height h, and your classmate measures how long that took you with a stopwatch or an iPhone. Remember that as you go up these stairs, you're gaining gravitational potential energy. You're using up chemical energy, of course, which becomes kinetic on the way up, and that then changes into gravitational by the time you reach the top. That gravitational potential energy, EP gained, of course, is given by mgh, as you now know. So the purpose of this experiment is to measure your personal power output. And all power outputs, P, are given by work done divided by time taken. Well, how much work do you do when you're walking up the stairs? Well, remember that work done when you're going vertically upwards is gravitational potential energy gained. Now, don't worry about the fact that you're kind of going diagonally as you go up. It's only the vertical height that matters, okay? So even although you've got little horizontal movements every time you go up a stair, they're not in the equation. Only the vertical height gained is in the equation. Therefore, it's the 10 meters as shown. So your power output is gravitational potential energy gained divided by time taken, which is mgh over time taken. So when we do the experiment then, if you measure your mass, and you know the gravitational field strength of the Earth, and you measure the height you've ascended, and someone times you to do the ascent, putting all of these together into the equation, you can work out your own personal power output. And that's what we're now about to do with some sample data. I've chosen some average sort of results, having done this many times over the years. So I'm assuming your mass is 50 kilograms. The height ascended is fixed, it's definitely 10 meters, I've measured that. And a typical time would be maybe around 15 seconds. So your task now, using a calculator, is to calculate the personal power output of this 50 kilogram person ascending from the ground floor to the physics lab. Pause the video now and work out your personal power output. Well, you're going to use the standard power equation. Power equals work done divided by time taken. Because we're going vertically upwards through a height h, we can convert that into potential energy gained divided by time taken. And straight away we know that that's mgh over time taken. All that remains then is to put in the values, substitute in the values. We get 50 times 9.8 times 10. Divide all of that by 15. And your power output is 327 watts. And that's fairly typical for a pupil ascending 3 floors. Some do it a bit with a slightly higher power output, some do it with lower. Note though that this is a much higher power output than when we were shopping. The reason for that is that it takes really quite a large force to lift a 50 kilogram mass. It's just under 500 newtons, whereas the force to push the trolley was quite small, about 50 newtons. So much bigger force. And also, we ascended these stairs in only 15 seconds, whereas it took us 20 minutes to go around the supermarket. So big work done, small time taken, large power output. So that is how you work out your personal power output.